It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Farmers Really Nice Coffee.
Hi guys, welcome to the fifth video in the organic chem topic. This one is all about carboxylic acids. Now, if you know your superheroes, you will hopefully know that this is Ant-Man, and you might be wondering what he's got to do with carboxylic acids. Well, the very first carboxylic acid that you can encounter in the homologous series is methanoic acid, and the common name for methanoic acid is formic acid, and where you will find formic acid is in ants. So I've tried to put him in just as a kind of an introduction to the whole thing. Plus, I also just think he's quite funny. So for carboxylic acids, they all contain what we call the carboxyl functional group. So the carboxyl functional group is made up of two things. It's made up of this C11O, which is called the carbonyl group. Okay, and it's made up of the OH, which is the hydroxyl group. So if you combine carbonyl and hydroxyl, you get carboxyl. That's why we call it a carboxyl group. Now, it's a very, very polar group. Okay, what you've got here in the carboxyl group is, if we're drawing this carbon here, you've got this oxygen, which is delta negative. All right, it's more electronegative than the carbon. So this oxygen is going to draw electron density away from the carbon atom. Now, this oxygen here doesn't have as much electron density to draw from the carbon, because this one's taking more of the electron density away. So what that means is that this oxygen is going to have to draw more electron density from the hydrogen. Okay, so this delta positive here, this bond is actually more polar than you would find in the corresponding alcohol, because of this because of this polar carbonyl group that you've got here. So because this is more polar, the bonds that are formed, the hydrogen bonds that are formed, are stronger than you'd find in the alcohol. You also get two sites for hydrogen bonding here, as you can see, as opposed to a fewer sites in the alcohol. And so the carboxylic acid has a higher boiling point than the corresponding alcohol. So that means ethanol has a lower boiling point than ethanoic acid. All right. Solubility is around about the same though. The first four carboxylic acids are soluble in water. So the first four are methanol. I keep saying alcohols. Methanoic acid, ethanoic acid, propanoic acid, and butanoic acid. Those ones tend to be soluble in water. But as soon as you then add extra CH2 groups in, so you get to pentanoic acid and hexanoic acid, the solubility drops right down and you get two layers, just because you've got quite a large non-polar group within there. Okay. Now, they have an unpleasant odour and taste. So the best one is butyric acid, which is has a smell which you'll commonly find in vomit or parmesan cheese. That's a really good example. Ethanoic acid is actually a vinegar as well, so that has quite a strong smell as well, which some people don't quite like. So if you're having a look at the three-dimensional structure of the model, you can see it here. So this is actually vinegar, this is ethanoic acid, so we've got a CH3 group down one end, and here you can see we've got a carbon double bond oxygen, and I've used the purple bonds here to show that it is a polar bond. Okay, and I've got, it's really hard working with the camera, sorry, and I've got the OH there as well, so you can see we've got some polar bonds in there, we've got opportunities for hydrogen bonding across the molecule. Okay, and that's how it kind of exists. It's a trigonal planar arrangement around that carbon due to the double bond that's in there. All right, so that's what a ethanol molecule looks like in 3 dimensions. All right, quite often a lot of people think about it, it's like a bit like a dog with a wheel at the front. All right, so if these things are really great. If you haven't got a molecular model kit, they're pretty cheap off of eBay. Grab one and you can make lots of cool little things. They have a sour taste as well, citric acid, tartaric acid, think about those sort of things we use in food. They're quite a sharp, biting taste when you have them. So yeah, they're not generally that great. We know how to prepare them. We've looked at this in the alcohol and the aldehyde section. So we oxidize primary alcohols or aldehydes. You use acidified dichromate. You get a color change from orange to green. I've been through that before. I'm not going to go back over it again. Carboxylic acids are weak acids. Okay, so that means that they only partially ionize in water, and we can represent that through it is an equilibrium for ionization. So this is one way they've written it. Sometimes you might see it written like this, okay, with a dotted arrow for one way and then a solid arrow for the back way. So what that means is that in the equilibrium, the back reaction is favored, so you can have a lot more of your organic acid here than you are the carboxylate ion. So they only very weakly donate ions in solution. Carboxylic acids will react with bases. In fact, they have all the same properties as other acids. So I do have a video on just the basics of what is an acid, and they follow all those same properties. So they turn, obviously, indicators the colour of normal acids. So universal indicator goes red-orange colour. Phenolphthalein is colourless. You've got methyl orange, which goes red. Most of your indicators, litmus goes red in acids, so they do the same thing with the carboxylic acids. They react with hydroxides, which are a base. So the carboxylic acid gets deprotonated, so that hydrogen reacts with the OH group on the hydroxide to form water, and you end up with your carboxylate salt. Alright. In carbonates, it's the same sort of thing again. You just deprotonate the carboxylate ion, but this time you're forming carbon dioxide. Same with a bicarbonate as well, you're just forming carbon dioxide. These reactions are how you power a bottle rocket, which is what we've got here. You use generally vinegar, bicarb soda. The reaction between it produces carbon dioxide gas that shoots out the end of the bottle rocket here, and that the outward force of the gas pushes the rocket upwards. Now this is quite useful within organic chemistry, because when you've got something like this, so benzoic acid has an aromatic group in it here. This C6H5 group is very non-polar. Okay, and so what that means is that this carboxylic acid is actually insoluble in water. So if you react it with sodium hydroxide, you deprotonate the acid and you put a sodium ion on there. Now this sodium carboxylate here, this sodium benzoate, is now water soluble, and the reason it can do that is because of something called ion dipole interactions. So the ion on the carboxylate, the COO minus, alright, so that carboxylate ion forms bonds with the dipole in water. Alright, so you've got the delta plus in water and you get an ion dipole bond forming there. Now that's really useful within drug chemistry, because when you have a really big organic molecule like this, alright, there's a carboxylic acid group here which is polar, but then you've got a non-polar benzene ring here, and you've got an ester group in here as well. Now this is a very non-polar molecule, so that's insoluble. This is the structure of aspirin. When we deprotonate the acid and turn it into a sodium salt, though, we can form these ion dipole interactions with water. And what that means is that we've now turned this drug into a water-soluble form, which is really important, because if it's not water-soluble, it won't dissolve in the blood, and so it can't get around your body. Okay, so this is one of the two key ways that they make drugs water-soluble. The other one is with an amine group, which is the next topic. So I suggest that you just have a look at this, make sure you get your head around actually what is happening. So we're deprotonating the carboxylic acid by reacting with a base, generally a sodium or a potassium hydroxide, because the only other product is water. That forms a ionic salt, alright, which can form ion dipole interactions with water. So make sure you learn this terminology about ion dipole interactions, and that now makes the drug water soluble, which is really good because it can be absorbed into the bloodstream. Alright, hopefully this topic has made sense for you as well, this little section. Key things for carboxylic acids is being able to obviously name them and draw them, which is the same for any topic. Then it's how they're formed by the oxidation of aldehydes or primary alcohols. And then it's also around, really importantly, this reaction where we deprotonate the carboxylate acid to make a carboxylate ion and make a drug water soluble. As always, if you've got any questions, just ask. Thanks, guys.